Okay, well, it's 10:31. And because I don't know, from day to day, I never know exactly how many people are going to be in class. So we might as well start on time, and that'll also encourage everybody to get logged in a timely fashion in the future. Okay, let me show you a couple things on iLearn first so that um, everyone is noticing the changes that I'm making. Let me just share screen. Here we go. Okay, so this is in the week 1, lab 1 documents folder. And I just wanted to point out that for part 2 on the topographic maps, you have the exercise itself. I added in this example diagram, a drawing that where I've annotated. I'll just show you. So I annotated the diagram to point, the red arrows point at a similar feature all around this mountain in this question, and the blue arrows all point at the same type of feature. And the question is, where are the hills, where are the ridges, and where are the streams or the valleys? And so it asks you to think about the rule of V's, I guess is one way to think about it. So I wanted I referred to this in the forum, the question and answer forum. I've been taking some questions by email, although I think I finally realized at the beginning, for the most of the first week, that forum you were unable to post. I had to click some extra button before you guys could post. So, but somebody now has successfully posted a question, which is great. And I think that you all get an email summary of those posts at the end of the day or in the middle of the night or something like that. Let me know if I'm wrong. That's intentional so that you see the progress. But that's where I pointed to, like, okay, I gave you an example here. Go take a look at it. Maybe that'll help you answer the question. But also to that's what's possible in Google Drawings. When, if you want to do your labs electronically completely, what you can do is simply, because I give you like a Word document to start with, essentially, you can click on the images or the individual small maps that are in your lab, copy those, and paste them into a Google Drawings page. So it's all done online. And it has enough functionality with like lines, different types of lines, like straight lines or custom lines or arrows, boxes, circles, basically, and you can type. So that's basically everything that you would need in order to answer a question like on this topographic maps diagram. So I encourage you to, if you haven't used a drawing program like Adobe Illustrator before, there used to be Corel Draw. I haven't seen that one in a long time. There are other like free drawing apps that you can get all over the place. But Google Drawings is free, it's online, and you can save the images just like I did. I think your choice was a JPEG. You're given a choice of a JPEG or a PDF when you download from Google Drawings. And so then you can like pop that image, that drawing, right back into your lab in place of the original question as your answer, or at least part of your answer. I mean, you can also type so that you can, put an arrow to something and then type, this is the stream, or stream, to be clear. So the annotations sometimes are pretty critical to understanding the drawings. So consider that. And then I've given you a link here to an actual Google Drawings page. So you get a page like this, and you can try opening a file, which it probably opens any kind of PDF, JPEG. I don't know what other formats it accepts, but those for sure, probably like a GIF. And then, or you can insert an image that you like upload from your computer. anyway, so text box shapes, so just drawing simple lines. It's got these pull down menus, super easy to use. This is for a text box, so you can just start typing whatever you want. And if you don't need that big a box, you can just adjust everything. It's just a nice little program. Any questions about that? Like how maybe I should go and show you exactly what I mean by like copying the diagrams. Let me stop that share and start a new one.
I have a question.
Yeah, you got it. What?
I noticed on the iLearn it said to insert that JPEG into our lab. I turned the lab in this last weekend already, but I indicated like where the ridges and valleys are in writing. Is
That's
that okay?
yeah, absolutely. If you
Okay.
don't, I mean, if you don't feel comfortable, although I think you ought to give it a try, because I think having the ability to deal with diagrams electronically like that and to have a program where you can make it look nice is a great thing to use in your papers throughout college. So
Because some of the images, like I drew the profile
yeah, let me go.
and all of that. Like I did copy and paste yeah, I did the profile there, the topographic profile.
Right.
Like I just copied and pasted the images into Word because you can do drawings and stuff in Word.
Totally.
I put them back in the lab. So
Totally, totally. If you have the patience to deal with drawing in Word, go for it.
okay.
I have struggled trying to get, because what I find is in Word, when I try to do this, it doesn't want to draw on top of the image sometimes. It like makes the image jump all around and you're like, tearing
Mhm.
your hair out, or at least that's my experience.
Okay,
Um,
well, I'll just use Google Drawings next time. I just didn't know about it.
no, don't worry. You accomplished it just a different way. I actually thought you meant that you hand drew your answers, which is fine too. You can print these if you want, hand draw on them, and then you can scan or take pictures and then create a single PDF out of that.
Okay.
If anybody needs help with that kind of technical stuff, ask me those questions, because I mean, sometimes I can answer them and sometimes I'm like, here, let me Google that for you, because that's what I do if I don't know. So, but I'm willing to answer those questions and try to help you out, because like I said, it's an important skill to have.
Mhm.
Anyway, yeah, you can do the same exact thing as you simply click and then you would Command C, or it's Control C on a PC, and then you just copy and paste into your Word document, your page
Mhm.
document, Google
Yeah,
Drive.
that's what I did.
It's totally fine. All of the above are fine. It's whatever you like best, and I'm just trying to point you to what I think will be easiest for you.
Okay.
Okay, so that's what I meant there. I'll just, I'm going to leave up, but let me stop that. I want to go back just briefly to iLearn, go back to the main class. Nothing up here has changed. I wanted to show you, if you haven't already noticed this, that you can collapse these weeks or these sections, so you don't have to keep looking at them and you can get right down to where you need to be. But I wanted to point out two things. I couldn't figure out how to force iLearn to let you submit twice in one link, like in one submission, one activity, whatever they call it on iLearn. You could do multiple files at one time, but once you submitted, you're submitted. So I just created a second link for the second part on topographic maps there. So you can do lab 1, part 1 on observations, interpretations here, and lab 1, part 2 topographic maps. I didn't want to call it lab 2 because I was trying to keep the labs the same numbers as the weeks, as to not be confusing. So that's why it's part 2. don't worry if you haven't finished that yet or even gotten very far, because the lab that we'll do on Thursday, that will start on Thursday, there's no pre-lab. So the one will start on Thursday, I think, and this is my guess, and we'll see if how good a guesser I am. That lab won't take you very long. And so you have time now and until Thursday, certainly, to finish your topographic maps lab. And hopefully, but like I said before, late work is okay if you can't get it done before Thursday. You need the weekend or something, that's fine. Take the weekend and then upload it. There are a few new people in class that might have joined us this morning. A couple of not too late ads, but notice that I give you a target deadline. So the target for the second part of that lab is Thursday, but like late work is okay. Also, I did finally go through on iLearn, and for each grading category, so for your labs, for the online quizzes, and for the larger quizzes or the exams is what I call them on the syllabus. And we'll have maybe 5 of those. So maybe every 3 weeks or something, we'll have a larger quiz than the online ones that's cumulative to that point. So like if we do the first 3 weeks, then I'll test you on that first 3 weeks of content. The second exam would be the second 3 weeks of content, that kind of thing. But in iLearn, I have made it, can't think of the word, chosen the right options so that it will drop your lowest 2 scores for each of those categories. Which means either your actual lowest 2 scores, or it means that if you can't get a lab done one week, it's okay. You can use one of those drop 2 lowest scores. So hopefully that will relieve some pressure on you guys to get all these labs done on a weekly basis. If you get behind, you can drop 1 or actually 2. Questions about that?
So you said that we're going to have a larger quiz. Is that going to be like synchronous or asynchronous, the larger quiz?
Everything about this class is going to be possible asynchronously. So I think what that means is I think it ought to be asynchronous for everybody, because I can't think of a way to do it synchronously and include everyone who's not there at the time we have class. So yeah, but I'll probably I'll probably try to take it easy, like on the lecture content that day, give you a little bit extra time to dedicate to the asynchronous exam. Okay. There's nothing on the schedule yet about that. There's nothing on iLearn about that yet. It's just like, as soon as I can get to it, I will create those. But it's going to be around the end of week 3 or week 4-ish. The first one might be a little late, like until I get oriented here. Anyhow, okay, so I'm going to collapse that for now. Just don't forget that. Oh, yeah, last thing. I said 2 things. Was that and the survey. I don't have everybody's survey yet. Please, the new people who have added this week or today, don't forget to fill out that survey. Again, I ask you to do it by today, but it's okay if it's by the end. It's okay if it's next week. I just need the most important thing, apart from knowing what you want me to call you and all that, is I need your address, so that our department technician, Russell, who's here, I think most days he's here now. We all just, like literally this week, or maybe it was the end of last week, got permission to come back on campus at all. So yeah, there's some people back, but not very many. I still don't see anybody in the hallways. Anyhow, Russell's here, and he's already started putting your boxes together. He's adding, this is to complement the rock and mineral kits that I asked you to buy. So he's adding a thick glass plate that you can use to test hardness, a magnet to test magnetism, a dropper bottle that I hope we can fill with 10% hydrochloric acid. They're cute little tiny droppers. They are, they're not going to include a lot of acid. And if we do get the permission, I think Russell, he wasn't getting a response out of the risk management people. And so he finally said, if I don't hear from you by X date, I'm going to just go ahead and do this. So if we don't hear from them, we have permission. That's how we're dealing with it. Anyway, he's going to pack it in some absorbent something or other so that should it spill on its way to you, it gets absorbed and doesn't do anything.
Professor?
We use this stuff in intro labs all the time. I get it on my fingers. It dries your skin out a little bit. It doesn't hurt. It doesn't even sting. It you know, if it sat there in a puddle on your skin, yeah, it might do some damage. But if you like get it out, wipe it off your hands, wash your hands, you're good to go. The only other thing is it does bleach clothing. How do I know that? Taking acid in the field as an undergrad and storing it in the back pocket of your backpack. And when it leaks, eventually you get a hole and lose the acid. But that it bleaches first and then it creates a hole after a while. So that is one side effect. However, it's such a small amount, it would spill. He's sending between 2 and 3 milliliters. So it's a tiny, tiny amount. And should it spill like on your coffee table, like you could clean it up very quick, like with one paper towel, you'd be done. Okay.
Question.
Yeah.
So it was regarding the survey. So I know that you said like that after you complete the assignments, they have a little like check mark next to them. So I did submit the survey. However, when I did that, there was not the little check mark. So I was unclear if it was actually submitted or not, or if I should redo it.
Oh, some of them are manual check marks. Some of them I set so that you check it when it's done.
Oh, okay.
So maybe that was a manual checkbox.
Okay, thank you.
Sure, yeah. So if it, but if it does, I will go back and double check that and make sure that it's set to the right thing, because that would be a lot easier if I just set it to, I'm gonna leave myself a note. If I just set it to automatically click that box for you when you submit. So thanks. Okay, cool. All right, so I'm gonna collapse this now. Any other questions? Should stop looking at that for time.
Oh yeah, I have like a question about like the supplies if it gets shipped to us.
Yeah.
Do we like after the lab, are we gonna like ship the supplies back, or is like
no, these are for you.
Oh, okay.
No, that would, I mean, it's not like these aren't expensive supplies. We're just sending you what you need to get your labs done. Yeah, it's for you to keep. You can dispose of the hydrochloric acid. You can dilute it in water and just pour it down the drain. It's strong lemon juice. Okay, let's see. So today, I guess before we get going on Earth history and the structure and the chemistry of the Earth, I want to take any questions about the Topographic Maps lab. I'll stop sharing this window and maybe I can, I'll do this. I will share the lab again and just scroll through this and see if there are questions about anything I can clarify about the questions on here or exactly what I'm asking you to do. So if you've got questions, hit me. You can unmute yourself.
I actually have a question.
Okay.
I was actually confused on which map you wanted us to focus on. I was hoping if you can clarify which one.
Okay, for this question right here?
Yeah.
So it's asking you, so the question is asking you to use both of these and to say, of the two parts of topo maps, I'm going to say topo map instead of topographic map because it's easier. So these two sections of topo maps, it's saying one is steeper and one is shallower. And it's asking you to look at the spacing of the contours. So these lines of equal elevation. So this, it looks like these are probably, it's in feet. So even though when, as scientists, we should be using the metric system, a lot of things that are still produced in the US use feet. So topographic maps are one of those things. So 400 here, 420, 440, 460, 480, 500 feet. So that has 5 contours in the same distance between these two red X's as this one. So this has 2, and it's the same 20-foot contour interval. So 2 20-foot contours that are the same distance apart. So looking at that, it's asking you to evaluate which one is steep topography and which one is more shallow, more gradual topography. Do you want to take a stab at that? Do you want to think about that a little bit longer? You can, there, you have a couple of options. There are a bunch of, I'm just going to interrupt you because you didn't sound like you're going to dive right in there. So there are links in your lab. These blue things that are underlined are actually links to web pages that will discuss a lot of the ways that you should be thinking about contours, contour intervals, this rule of V's that it talks about later in the lab. So you probably need to go read some of those pages. So there's one here, there's, oh, that's the same one, I think, contour line maps. Yeah, that's the same link. That might be even the same link. That's a different one, constructing a topographic profile. So this one specifically helps you with this question, the 4th diagram, and then the others are from that same page. So you might want to read that. The other thing that you can do is a mental exercise. So you can set up 2 chairs in your living room that are 20 feet apart. If you have that much space, or 10 feet apart, we can have it. And think about whether, if you're standing here and you're looking at that chair over there and you're the same distance apart, now imagine that I'm on the right-hand side map. I'm on this contour, on this right-hand X, red X, and I'm looking over there at that other X. And if there's a difference of 20 feet in elevation, so let's say it's 20 feet below me over there, versus this map, same mental exercise, same chairs, I'm standing on this red X, same red X, or plus sign, or whatever it is. I'm on the same plus sign, and I look over there at that chair, and instead of 20 feet below me, how many feet, oh, above me? Look at that, it goes up. Instead of below me, it's above me. So instead of 20 feet above me, it is how many feet above me?
Oh, 100?
Yeah, 100. So you go from 400 to 500 feet. So instead of 20 feet above me, it's 100 feet above me. So which of those two represents steeper topography based on that mental exercise?
The 400 to 500 one?
Totally. So if you're going to turn that into like a rule and a way of thinking about contours and contour intervals, This, with the closely spaced contours, represents steep topography. Sometimes they get really close and you're basically looking at a cliff, like when they almost touch each other. Versus this, which is, it's 20 feet above you. It's still not nothing, but it's a lot less than this one. So yeah, that is how you answer that kind of question. So great. I think it's better to do the mental exercises if you're able, if you've got some spatial thinking, and I hope that you can practice that in this class because it's important for looking at maps and satellite images. Okay, so how can you tell? How you can tell is that these contours are closely spaced compared to that map. That's what I'm asking for in that question. That's how you know. You could also add in, I did the mental exercise, or I read the link and I learned that closely spaced contours means steep topography. Okay, so let's look at this last part of the question just to be thorough. Because the steepness on a topographic map is the amount that the elevation changes over a given horizontal distance, you can use the contour interval in the map scale to measure the steepness between the marked points on each map. How would you go about determining the steepness between the 2 points by the red pluses on each map? I could simplify that question and basically ask you to tell me what the slope is between on the left-hand side map versus the right-hand side map. So do you guys remember how to find a slope mathematically? It's okay if you don't. You're going to need, well, there's a formula, y equals mx plus b. We don't necessarily have to graph this, although we could graph it. You're looking for m, you're looking for you need to know the distance in the x direction. So the horizontal distance between the 2 points. So that would be literally measuring between here and here. You have a scale to use. So it's not like, oh, that's an inch when I print it out. That's not what it means. It means, look, using this scale right here, that this distance is a half mile. So you would get a ruler and see what measurement that is, compare it to the 2 red X's and figure out how far apart they are. It looks like they might be really close to a half mile apart. So we could just say, let's call it a half mile for now. So that's your distance in X. And then your distance in Y is your vertical distance. So that's your elevation gain from 400 to 500 feet. So it's 100 for that. So it's a half mile in X direction and 100 feet in the Y direction. We're going to need to do some converting of units. So we'll need to figure out how many feet are in a mile so that we're using the same units when we do this. I think I might need to work this out with you, not for you, I'd rather with you. Can someone Google real quick how many feet are in a mile to just give me that number?
5,280.
That's what it is, 5,280. Okay, I don't know. It's pretty small, but maybe you can see. Can you see that?
Not really.
Okay. Okay, let's see. Let's see. I need like a little sticky note or something. Or a new page here. Okay. Bear with me while I find the right thing in. I need to stop sharing that. I'm going to try to share this page instead. Okay. I have a little drawing tablet here, so I'm gonna try using this and see if I can't draw on this screen. Let me find a tool that I can use. Does it not have the right thing? Okay, forget that. I'm gonna have to open Adobe because I know that'll work. Give it a second to open. Okay. Here we go. So let me, I'm going to copy and paste those diagrams here. New. Okay. Use a pencil tool. Okay, so, let me paste those two diagrams and make that bigger so you guys can see. Okay. Actually, you know what? I didn't do that using the right tool. I want this to stay to scale. There we go. Okay, so here's the same problem. We need to know, okay, I'll try to use this. Y equals, oh, there's no color in my line. Y, okay, equals mx plus b. That's if we were gonna graph it. That is the formula that we would use. Now, for this example, I'm trying to give you, we're trying to find x, which is the horizontal distance. So if you were going to look at a plot, it would look like this. I still don't have it. Okay. Let me make those lines bigger. Okay. So you could plot this on a diagram like this. So your horizontal distance would be on the x-axis. Let me just draw. Okay. So this is x there. This is y. So your vertical distance you could plot on your y-axis, your horizontal distance on the x-axis. So we called that a half mile and 100 feet. We'll come back to this because I just realized we didn't start here. I was going to explain unit conversion. That's right. Okay. So, okay. We have 1/2 mile equals, and we need to be able to cancel out miles. So miles needs to be able to cancel out. So we need, so we need a denominator that has miles in it. I'll put that over here. Miles. So how many feet per mile? It's 5,280, I think is what you guys said, feet per mile. Right. There we go. Okay. So now when we do the math here, oh, I guess I didn't, well, okay. So we need to know what to multiply. Here, let me take a step. Sorry. I need more space to work. I need a new page. There we go. Okay. Where'd my page go? There we go. Take this stuff, copy, page. Okay, I should actually ask you before I just like wing out and do this. So a half mile doesn't equal 500 and I shouldn't have put an equals sign there. What I meant to do was, let me just get rid of the equals, that'll help. We need to multiply the miles. Forgetting which one I'm working on. Oh, pencil. Come on now. I had you a second ago. I don't understand what it's doing. Okay, why is it doing that? Okay, I'm going to describe it now because for some reason I'm just getting beeps when I click on my Adobe screen. That's how you convert it right there. The equal sign was wrong. I was stuck on y equals mx plus b and I wasn't doing that right. So a half a mile, to convert that into feet, you need to be able to have a conversion. So this is your conversion unit. So 5,280 feet in 1 mile. So I just left off the 1. So you could say per 1 mile. Then you would multiply a half mile times 528 feet per mile. The miles cancel out, and then you're left with the answer. So a half mile is how many feet? Someone already put it in the chat box, actually, didn't you? I had that open a while ago. It's 2,640, right? So half of that. So it's when you multiply there, it's just like putting the 2 in the denominator, right? So you're just taking 5,280 feet divided by 2, essentially. The ones cancel out, the miles cancel out. Okay? So we should be using the same units when we do this. So we had a half mile in X. This is taking a long time, isn't it? It's okay, we'll take the time. We have a half mile in X, horizontal distance, and we had 100 feet. So now we know that the half mile is actually 2,640. Is it still gonna beep at me? It still is. I don't even know how I can close it. What is going on? Okay, we're just gonna force quit this. So sorry, I can't. Sharing anymore. That's okay. So what is the slope is the question. You would need to know how many feet in Y per distance, like a unit distance. So you'd be essentially dividing the 100 feet per half a mile, or 2,640 feet. That should give you a slope. Now, if you do the same thing for the other diagram, I'll come back to this diagram. Let me share this screen again. I come back to this diagram. So we were trying to calculate this. So we were saying 100 feet in half a mile. That's how you like think of slope. I guess we can probably not even worry about y equals mx plus b. We can probably like forget that. That's how like algebraically how you would solve it. Probably we can do this as another mental exercise where we just want to know how much elevation gain is there for every bit of distance that we're walking. So put your elevation in the numerator, put the distance in x in the denominator. Make sure you're using the same units, and that should give you a slope. Does that make sense to everybody? And does it work? I'm going to keep the chat open just in case you guys are putting stuff there. Now do the same mental exercise for the right-hand diagram. The answer, there's one question I haven't answered in the chat, and it's, will I post this to Zoom? Yes, this is recording, and I'll put this on Zoom after class. Okay, same mental exercise. This time it's the same distance, right? It's a half a mile, but instead of 100, it's how much? Your contour interval is 20 feet, and here are two contours. So how much vertical distance are they apart? You can do in the chat, or you can unmute yourself and volunteer.
20 feet.
Yeah, 20 feet. So instead of 100 feet, it's 20 feet. 20 feet divided by that half mile. So 20 feet divided by 2,640 feet. So what is the numerical value for the slope in each of those cases? What I'm talking about is actually dividing 100 by 2,640 and then doing a separate calculation, which is 20 divided by 2,640. Each of those numbers should indicate a slope, and that's how you answer this last part of that question. Okay. So I'm going to let you work those out on your own. If you are struggling, you can always come back to this video and watch the explanation again, even though I stumbled through Adobe Illustrator. And I've used that program for forever too. I don't know what's going on. We can look at this diagram real quick and make sure everybody's on the same page with this one. So the topographic map shows, okay, someone wrote 0.04 for the steeper slope. And then there'll be a different answer for the gentler slope. Okay, the topographic map above shows a hill with a peak elevation of 2,574. It's marked right there. Here, I'll zoom in a little more. Okay, so 2,574 right at the peak. It's marked with an X above sea level. There are 4 valleys and 4 ridges that radiate from the peak. So it says, where are the ridges and where are the valleys? That's where that diagram came in before, and I saved it right here. Let me just switch over. So using Google Drawings, I showed you this earlier, I marked the 4 similar features in blue and 4 similar features in red. And the question to you is, which of those is a ridge or a hill? A ridge is more appropriate because a hill is like, you think of one point at the top. In this case, we're talking about like a long, steepish thing. Well, it's a long, gentle ridge maybe that you'd walk out along, but it's steep on either side. Versus a stream or a valley coming down from those peaks. I encourage you to do another mental exercise, even though that web page that's linked to the lab does go through about this rule of V's and try to get you to learn those things. But that's more like memorization. And I guess I'd rather have you look at the map and try to do a mental exercise and figure it out. So in this case, I guess I would either put myself at the peak and looking down this red arrow, or looking down. Oh, I put the arrows in different directions too. Okay, so either down this blue arrow or down this red arrow. And imagine seeing, now that we understand like the fact that more closely spaced contours represent steep terrain, and the gentler terrain is represented by contours that are spaced further apart. And so when you look at this hill, this mountain, it's definitely steeper here compared to the others. Yeah. And look down. So down this red arrow, it looks pretty steep because they're closely spaced. Looking down this blue arrow, it's further apart compared to either side. The contours are spaced further apart compared to either side. So if you're standing at that peak, you can imagine looking down, you know, we'll call this, you know, it's probably, if it's a 20-foot contour interval, it's something less than 20 feet. You know, it starts to drop off closer to you here compared to here, if you're standing up here. So if that contour is closer to you, that means it drops off faster from you. So it means it's a further down than if you were standing here looking down the blue arrow. Looking down the blue arrow, the contour is a bit further away from me. So that means it's gentler. I can, if you were going to pick a place to walk, you'd pick the place with the contours that were spaced further apart, unless you had like climbing equipment. You wouldn't want to walk down this necessarily. You'd probably choose something that was more gently inclined. So see if you can do that on your own. You can also change your perspective and do a mental exercise starting down at the bottom, or down here at the bottom of the blue arrow and the bottom of the red arrow. And then look up at the mountain, and you have to start imagining in your head, okay, what am I seeing when I'm seeing these closely spaced contours? You're seeing steep terrain. And with the contours pointing in this, well, I don't know which you would call I don't want to bring in the rule of V's because I don't know exactly how they phrase it, and so I don't want to like mess with anybody's understanding. But it points away on these sharp sides, right? It kind of looks like an upside down V. So when I'm looking up that mountain, I'm seeing steep terrain, and I'm seeing it move off to the side. It's also kind of steep on the sides of that steep terrain. Versus standing down here, you're looking up a gentle slope, or a gentler slope toward the peak. If that doesn't help you visualize, then I suggest going to the web page link. Any questions about this diagram before I close it? I'm going to suggest that you go to that Rule of Contour Lines Maps link and read how they describe that. Okay. Just share this real quick. I feel like if we need to take the time to talk about these labs during the lecture part of our class, then we'll just do that, and I'll leave content out of the lecture. You know, not every slide is critical. There are some that are more critical than others. So I'll try to edit what I was going to say today about Earth history, the chemistry and structure of Earth, to accommodate this. Okay, so it asks where are the ridges, where are the valleys, then refer to this Rule of Contour Lines Maps. That's the one I'm talking about. Follow that link and go read. Together, hopefully the visualization and the reading will help you to interpret these maps. I don't want to give it up just yet. I want you to work on it yourselves first. Okay. This one is asking you, okay, so it's putting it's asking you what are these features A and B? And I mentioned this last week, but you might need to read that page again to refresh your memory. It shows you that there are a couple of streams on the map now. And it asks you, one of the questions asks you to fill in the blanks here on the contours where it looks like they've erased a line there and there. They've basically taken out or covered up the contour label. So one task is to write in the elevation on those contours. And you're given a scale, similar half-mile scale again, and you're given a contour interval of 20 feet. So your job is to interpret that map and then figure out, do I count up from 1040 or down from 1040? Because that's the only one you're given. So it's kind of like a little puzzle. And hopefully it's a fun challenge and not a frustrating challenge for you. Okay, that's that one. I'm gonna leave the profile until Thursday so that we have time to talk about Earth history today. And plus this is like a different skill, and so I don't wanna start it now. So if you haven't done the lab yet, haven't finished the lab yet, and you were struggling with those first 3 maps or the first 3 diagrams, go ahead and work on those, finish those now that we've talked about it. Go read that link, finish it off. And then I encourage you to read this before coming to class on Thursday if you're gonna come back. And then we'll talk about constructing one of these profiles. The long and short of it is you drop straight lines down to the appropriate elevation on the graph here. You just drop the contours down. You drop a line straight down and mark it at the right elevation. Drop it straight down, mark. Drop it down, mark. That is, because I'm pointing here because you're going to go between A and B. So you're drawing a straight line, and you can draw on the diagram or use Google Drawings to put a line there. But a straight line between those points is where you're constructing this profile. So you drop the line down, mark it at the right elevation, drop it down, mark it at the elevation. Use a ruler to do this if you're doing it by hand, or make sure you're using straight lines and that they're horizontal, perfectly horizontal and perfectly vertical to do this lab. And then you will connect the dots basically to create the profile that shows this landform. Okay? And then, yeah, again, this last little bit, we'll save for Thursday. But see how much you can get done between now and then. And if you're able, if like 80% of you are able to complete the lab now, that would be great. But I'll certainly take questions and talk more about these on Thursday, okay? Any other questions before we move on to the lecture? Okay. If you need to get up and take a quick break, go ahead and take 2 minutes while I have a sip of Coke and get the lecture ready. Because it's drying. Okay, let me stop here. I'll just narrate, why not? Okay, get rid of the iLearn page. And oh yeah, so someone asked if we have any more questions, can we do Zoom one-on-one? Yes, of course we can do Zoom one-on-one. I will stay on Zoom until 12:30 today, even though I'll end at noon. I will end at noon today. I'll stay on for that half hour after. So you're perfectly welcome to stay with me and ask questions about the lab. Every Tuesday and Thursday, I plan to at least have that half an hour. And if there are more of you waiting to ask questions, I can take longer than that. We can spend more than that half an hour, or we can make an appointment sometime and we can Zoom one-on-one, or even in a small group if you guys know each other, that's fine. Okay. Okay, so close that. Okay, so here we go. Okay, hopefully everybody is back in the room. Okay, I put the map here on the front. It could have been a cross section through the Earth, I suppose. You see the crust, the mantle, and the core. But I decided to put a topographic map because literally the structure and the chemical composition of the crust and the underlying layers create what we see on this map, create the topography on the land, and create the bathymetry in the ocean floor. And let's see if I can figure out how to, what I want to do is annotate on this diagram, and I think I can. Oops. Problem is, there we go. Oh, yes. Mouse. Okay, I think I'm going to use, do you guys, you've been in these classes before, is the spotlight best? Is the mouse the best thing to use? Let's see what the spotlight looks like. Oh, here's an arrow. Oh, this is goofy looking. Let's try the arrow. Okay. Mark something that you can follow around. Okay. Never mind. I want the mouse then. Okay. Can you see a mouse? I certainly can't. Oh, God. I'll try drawing then. Oh, this is terrible. I don't know why this won't work. Okay, things aren't working for me technologically today. I'm just going to close out of here and forget it. I'll describe this instead. All right, what I was going to say is that the brown parts along the edges of the continents represent the high topography. I suppose it's red colored. You're seeing red, orange, yellows in the high topography in the plateaus. So the western part of North America is a result of plates colliding. It's a result of, in many cases, pieces of continent colliding over geologic time, oceanic crust being subducted or pushed down beneath the continent and scraping islands and long chains of islands off onto the edge of the continent. And I also wanted to point to the ridges within the seafloor. That's really what I wanted my pointer for. Instead, I'll describe the light blue colors that you see in the seafloor. Those are the high points. So those are the mid-ocean ridges that it's not always in the middle, right? In the middle of the Atlantic, certainly, that divides North America, South America from Europe and Africa. Those ridges are high points for a reason, because of the heat, the internal heat and the chemistry of the rocks in those places. So that's what this lecture is about, really, is explaining how we got here with how we started off, where Earth started off, and how we got to what the continents look today. I'm concentrating very hard to close out of this because it won't let me progress. Oh God, I'm getting the beep again. Okay, I'm gonna have to reshare that. I was stuck. What a pain. Okay, I'm not gonna try anything again. We'll just like go through the slides. I'm not gonna, no fancy tricks. Okay, please use, I'm gonna open the chat. That was supposed to be a question, but I accidentally clicked on it because I can't see the question right now. What explains why the ocean basins look the way they do? And you just maybe saw, maybe you blinked, but I wanted you to vote. Do you think it's meteorite impacts? Do you think it's continents moving around? Do you think it's a cooling Earth or an Earth that's warming? Well, it's continents moving. And that mid-Atlantic ridge that I was just explaining is there because continents, there has been new crust forming along that ridge. And every time new crust forms, it pushes the old crust out of the way. And so you're pushing the continents of North America, South America away from Africa and Europe. And all of the mountain ranges, whether they were in the ocean floor, those mid-ocean ridges, or whether they're on land, like those high points, the plateaus and the high peaks in the reds and oranges on the last map. Here, they're in green, the largest ones anyway, and some of them are covered up by some of these symbols. Just let's decipher these symbols first. Look at the bottom for the legend on this map. Every map should have a legend that explains any symbols and any terminologies or abbreviations that it uses. Should also have a north arrow, but in this case, I think we know where north is. The divergent boundaries are marked with a simple reddish brown line. And again, I wish I could point, but I'm not able to. I'll try again with this. It's not going to work. Okay. So look in the ocean floors, and those are the red lines that are the thin red lines that indicate a divergent plate boundary. So divergence is to spread apart. I'll just keep track, and maybe if I can use a thicker line, I can do something like this. When you've got plates moving apart, hopefully you can see that it's divergent. When the plates are, I've got to get this drawing pad working because this is not going to last long this way. If the plates are coming together or colliding, they're called convergent. And if they're sliding past one another, there is horizontal motion, not vertical motion. That's a transform plate boundary. So the transform plate boundary you should be familiar with because that's what the San Andreas Fault is. It's a transform plate boundary. And even though I was talking about on Tuesday last week, I mentioned that the Hayward Fault, the Calaveras Fault, the Rogers Creek Fault, all the Green Valley Fault, all these faults that are throughout the Bay Area, the ones even that are offshore a little bit, the San Gregorio Fault, all of those that are you find from the west part of the Bay Area all the way to the eastern hills, beyond, you know, like on your way to Sacramento even, those last hills as you come down out of them, that's kind of the last bit of this plate boundary. All of those faults they mostly have horizontal motion. They're mostly sliding past one another. And that whole space is the plate boundary. It's not one single line that you can put your finger on. It's a wide zone that is tens of miles wide. That's just because it's messy. In real, you know, when we draw these diagrams, it's nice and neat, and we draw a single line, and we call that the plate boundary, but it's messier than that. The divergent plate boundaries are mostly in the ocean floors. Mostly those are the mid-ocean ridges. The convergent plate boundaries are mostly where you find mountains. So, and often on the edges of continents. We've got older mountain belts, or like recorded through geologic time, we've got older mountain belts inland from the edges of these continents that are also old records of continental collisions. But these green areas like the Cascades and the Rocky Mountains in Western North America, the mountains up in Alaska and down through the Western Canada, Those are all part of, over time, adding on to the, building the North American continent by adding on these small pieces of island arcs or small microplates onto the edge of the continent to build it up to what it is today. Those are the collisional boundaries. And that's the kind of stuff I work on for my research, actually. Everything from billion-year-old plate boundaries, which those mountains that you can see on the East Coast, I really wish I had a pointer. You can see some hills under the A in the second A in American and North American, down to the right of the E in plate. Those hills right there. That's what I'm working on. That's a billion-year-old boundary. Those are the mountains that formed when Pangea formed, when there was one giant landmass on Earth. And then when Pangea broke up, it spread apart along the mid-Atlantic ridge. And that's where we get this like diagnostic plate boundaries that look like puzzle pieces, like they used to fit together because they were fit together. That's a record of that. So the convergent, let's see, the transform plate boundaries on this map are in yellow. So they do show up here and there, and especially like the most common place you see a transform plate boundary is not like the San Andreas Fault, actually. It's more often found in these little segments on the mid-ocean ridges. Do you see, I feel like I've got to draw something again. I will solve this problem of drawing, and I'll get drawing on the screen, I promise. I don't know what's going on. Oh, and I've replaced this laptop. I've got a new one that I'm in the process of backing up this one. So hopefully the new laptop won't give me the same problems. Let's call this a divergent plate boundary. And here are the arrows indicating that it's moving apart. You can call that the mid-Atlantic ridge if you want. But notice that it's not a straight line on this map. These divergent plate boundaries, they kind of zig and zag. So there are these little offsets on the boundaries. And just look at anywhere stay in the middle Atlantic Ocean. So look at the segment between Africa and South America. There are these yellow lines that separate these offset parts of the divergent plate boundary. Now I'm looking for colored chalk. I don't have colored chalk. Wasn't prepared to do this. Okay. These are transform plate boundaries to accommodate these little offsets. You have to have a transform plate boundary to make this work, because this side of the plate is moving this direction and that side of the plate is moving in that direction. Do the same thing down here. This side of the plate is moving that way. This side of the plate is moving that way. So you need a transform fault to separate those. So most of them are small faults in the oceanic crust. And every time we just had one of these too, every time we get a rare occurrence of, well, they're not so rare, but it feels more rare compared to California. But an earthquake in the East Coast, like in North Carolina or New York, there was one in Washington, D.C. not too long ago. It may have been 5 years now, actually. But people were freaking out because they're not used to having earthquakes back there. What it is they're having earthquakes on weak parts of the crust that fall on these old transform faults that are offsets from the mid-ocean ridge. So there's a record that you can trace back all the way in the oceanic crust. You can trace it all the way back to the East Coast, and you see this, it's called a fracture zone. And you see that fracture zone basically butt up against the continent of North America. And it's right there where you get those, the epicenters for those earthquakes. Okay, the other thing that's on here are all the dots are earthquakes epicenters. So you see a bunch in the Himalaya mountains north of India. You see, you know, there are a lot along the San Andreas Fault. Basically, they're everywhere there's a plate boundary is where you find earthquakes. And there are little triangle symbols also all over this map. Those represent volcanoes. And those also fall all over these plate boundaries. So the convergent, everywhere we've got a plate boundary, whether it's divergent, convergent, transform, you're gonna get earthquakes. It's just the size and the location of the earthquake that changes. And everywhere you get a divergent plate boundary, I think this is true, you have volcanism. Even though there aren't really, they don't really show volcanoes along the mid-ocean ridges there, because it would just be all over the place. I think it's just, it hides the plate boundary too much. You wouldn't see any other detail. But the big explosive volcanoes that we hear about in the news, those are certainly marked. And those fall along these convergent plate boundaries where plates are colliding. Usually where oceanic crust is pushing up against continental crust, and the oceanic crust kind of loses that battle and gets subducted down into the mantle. Okay, enough on this diagram. I could talk about this forever, and we haven't even gotten to hot spots yet. You can see Hawaii and Yellowstone there too. There's a lot of information here, but the whole point was it's all because of the underlying features that we've got. So let's look at a cutout of Earth's interior. Oh, by the way, this time I got slides. All of these PowerPoint slides are on the iLearn page, so you can download them and make notes directly on the slides. You'll probably have more success than I am being on the screen here. Okay, back to the science. Notice that there's an inner core. And again, sorry I can't point. The white inner core, the yellow outer core, there's an orange lower mantle, kind of a reddish orange upper mantle, and then the crust. Those layers are all different in a couple of ways. They have similarities and there are differences in this. You're either the layer, you name the layers of the earth depending on whether you're talking about how strong they are. So whether it's the lithosphere, which is the outer cooled shell of Earth that is rigid and solid and not molten. This little profile that's the box that's the cutout, it's probably on this side of your screen, shows the lithosphere being composed of the continental crust plus a tiny bit of the upper mantle, the oceanic crust, and a tiny bit of the upper mantle. That's because even though the mantle is very hot, the rocks are not hot enough to overcome the pressures to melt. Because pressure increases as we go down inside Earth too, and the pressure suppresses melting to some extent. So we have this cool outer shell that is rigid. We call that whole shell the lithosphere. It's like the sphere of rock is basically what that means. Or you can talk about the crust, the continental crust or the oceanic crust, and the mantle. Those are different based on chemistry. The mantle, the whole mantle, even that part of it that's the lithosphere and the asthenosphere and even the lower mantle, they're all approximately composed of iron and magnesium silicates. Whereas the continental crust has a lot more silica in it, silicon and oxygen. in the minerals that comprise the continental crust. If you were to stir up the entire continental crust and try to name it one kind of rock, you could call it granite, essentially. You know, maybe it's got a little more iron or magnesium than a true granite, but it's a light colored rock. I'm saying granite because a lot of you probably, well, it might be misleading if you're thinking about kitchen counters, but you might be. And they call any kind of hard rock a granite, and it's like, it kills me anytime I go to one of those places and they're trying to sell countertops, and it's either they call like a ton of variety of different rocks only granite or marble, or there might be one more. There are only like 3 kinds, and that's it. It's ridiculous. A granite is a light colored rock. We'll get to this in our labs, of course. It's light colored. It's got a lot of feldspar minerals, quartz. It might have some pink feldspars in there, and maybe black flecks of some biotite crystals. You don't have to know these minerals yet, but if you do, great. Maybe some other little black minerals, but it's mostly light colored, and that indicates its chemistry to some extent. It's got more silica. It's got silicon and oxygen. It's got more sodium, more potassium, broadly compared to, and more aluminum. I would add that in there too, than the mantle. The mantle is iron, magnesium, silicon, and oxygen, basically. And then, so what I'm saying is we get different names to these parts, these layers of the earth, depending on whether we're talking about the rigid shell of the lithosphere, the mesosphere, and the core, or are we talking the outer core and the inner core, or are we talking about the crust, the mantle, and the core? Those are the differences. I'm going to show you more of this, and I have one in particular that I'd like to go to now, but I don't want to skip too far ahead and miss things. I'll show you one diagram in a moment that splits. One side it shows the strength of the earth, and one side shows the compositional terms. So this will be clearer soon. Okay, this I've already talked about. The divergent plate boundary, a convergent plate boundary, and a transform boundary. Here they are in diagram form so you can see what I'm talking about. If we start with a transform plate boundary, because that's what we've got here, notice that it's only that there are no volcanoes. There are earthquakes marked. Those are those little stars there, and it shows horizontal offset of that mountain range, or whatever that's supposed to be. That's a good description of what transform plate boundaries are all about. A convergent plate boundary, so where in this case, it's 2 oceanic plates that are colliding. The one that is comprised of colder, older, more dense crust sinks below the other one. And then you get melting above that subducting plate, not melting of the plate itself. It's actually a piece of the mantle that's melting, that sits in that little wedge above the subducting plate. That's where you get the volcanoes forming. And those are your mountains. That's the vertical building up of continents that you see in a convergent plate boundary. Then in a divergent plate boundary, you see, again, earthquakes, but in this case, they're very small magnitude earthquakes. You'd see melting in the mantle, they've labeled it a Lithosphere. That's an oversimplification. But the idea is that you're getting melted mantle, and it's in part because the pressure has been lessened at that point in the mantle, because there's new crust that's erupting on the surface of the ocean floor. It's making space for the new crust, the new basalts that are forming there. And that space that's created takes the pressure off the underlying mantle, just enough to allow it to melt. And that's where you get the the volcanism at a mid-ocean ridge, for example. We're going to go into these processes a lot more detail when we get to the plate tectonics lecture in 2 weeks. Okay, so which type of energy do you suppose fuels these processes? Because something has to be going on in order to drive these plate motions, to drive the collisions and the spreading. Where is that energy coming from? Is it heat and light energy from the sun? Is it from the Earth's interior? Is it from heat produced by burning fossil fuels? I wish that I could pull up, I don't think I can pull up the chat. I would ask you to vote. You can go ahead and vote for each other. Or you can do, let's see, how do we do this? I don't think there's a way to do it in the participants window. So I think the only way you can do is to chat. Does anyone want to take a stab to shout out what it is? Or can
B.
you, B, yeah, heat and energy from the Earth's interior. Yeah, definitely. I alluded to that, the fact that the temperature increases as you move towards the center of the Earth, and pressure increases. The pressure increases as you move to the center because you've got all of this rock on top of it. So that's just the pressure from the load of rock above it that are driving all of this. And certainly there are a number of processes that control that too. So let's talk about how do we get the heat from the interior of the Earth. So this is coming from, oh, you know what I didn't say, I just want to say, I didn't get to the core. And before I say this next thing in that last slide, I need to bring this up. So the plates, I'll go from top down. Looking underneath the continental crust, you see the bit of lithosphere underneath that. That's at the top part of the mantle. Underneath that, you see a asthenosphere. That is a semi-molten, gooey layer that the plates ride around on. It deforms. It's not molten. It's not like liquid rock down there. There's a small percentage of melt, but basically it's enough to coat the grains of the rock so that they flow very slowly. It's like really viscous, meaning it resists flow. It's like you think of like a honey that's been on the shelf too long, like something really viscous. It doesn't want to pour out. This doesn't want to move really, but the heat from the underlying earth is causing that small bit of melting in the asthenosphere that allows it to deform and to act like the jelly on a peanut butter and jelly sandwich. That you move, if you were to, like the top layer of bread, if you were to cut that in half and move it around on the jelly, that's the kind of idea. Although the asthenosphere is a lot more viscous than jelly. The lower mantle, even though it's deeper and hotter than the upper part of the mantle, the lower mantle is solid. It's completely solid because the pressure overcomes the temperature, basically. The pressure is too high, it suppresses the melting. The outer core, though, is completely molten. It changes composition, though. When we didn't go there yet, we'll get there. The outer core the whole core is mostly iron, nickel, and a few other things, maybe silicon, sulfur, oxygen, but mostly iron. So there's a liquid iron outer core that, because the Earth spins, the liquid outer core also spins and gives us our magnetic poles, the magnetic field that we have on Earth. The inner core, again, though, is completely solid. Again, the pressure overtakes, it's immense pressure at that point, overtakes the heat and whatever is driving the heat, maybe breaking down of radioactive elements could be driving some of this heat that's still in the outer core. and the inner core too. Okay, so the point is I wanted the inner core is solid, the outer core is liquid, the lower mantle is solid, the asthenosphere is gooey and plastic. It's neither solid nor liquid. And the lithosphere, that it's the uppermost part of the mantle, and the crust are completely solid again. Okay. You'll hear that again out of me. Let's come back here. Okay, so now that we've established that there's heat, that there are molten layers even, the outer core is molten because of that heat. So there's a lot of heat going on there in the inner earth. And some of that heat is transmitted through the layers of the earth by conduction. You know what conduction is. Metal conducts heat very well. So if you were to pour coffee into an aluminum camping mug or something, if you've ever done that, it's going to burn your hand because the metal of the cup conducts the heat away from the coffee quickly and it gets to your hand. That's the kind of conduction I'm talking about. However, rocks aren't good conductors. They don't conduct like metal does. So it's a lot slower process, and some kinds of rocks conduct that heat better than others. Okay, let's see, did I cover with, yes, I did. So that's one means of getting heat from the, wait, yeah, I said that, okay. So that's one way of getting heat from the center of the earth to the outer part. I put this diagram on here that shows temperature compared to depth. So, and it's broken this diagram into, look on the right-hand side of the screen, it's broken it into lithosphere, upper mantle, lower mantle, outer core, that's the liquid outer core, solid inner core. And look at the temperatures that it puts on there. Now it's using scientific units of Kelvin. If you subtract 273 degrees, wait, I'm making sure I'm going the right direction. Yeah, you subtract 273 degrees, that gives you a temperature in Celsius. So these are really hot rocks in the center of the earth, really hot, thousands of degrees Celsius. You know, to just gauge, 100 degrees Celsius is boiling water. So that's about 212 degrees Fahrenheit. So even though we, you know, it's hard, it's not automatic to convert from kelvins to Celsius to Fahrenheit here, we're still dealing with thousands of degrees Fahrenheit. So really hot. And I guess the point really is to show how the heat just increases rapidly through the lithosphere, like really rapidly. Sorry, I read lithosphere, I was looking at the upper mantle line. The heat is increasing really rapidly through the upper mantle, lower mantle, through the mantle. The lithosphere has a shallower line. The shallower line indicates it's a less rapid. It's a slower heating because the rocks on the crust are not good conductors. The rocks and the chemistry of the inner core, outer core, and mantle are a lot more conductive. So the heat is transmitted better through those rocks, and that's why you see the steep line increase from, let's say, 1900 Kelvin to 3000 Kelvin and on. So the steep line is a fast increase in temperature. The shallow line is a slower increase. Okay, and I think, yeah, I want to get to that diagram that compares the two side by side. That's where I really want to get today. Do I have time? It's noon now. Oh my God. Okay. Okay. I'll finish up in 2 minutes. Radiation is another way to heat something, to transmit heat. So energy is transmitted as waves, kind of like solar radiation transmit, like infrared radiation is heat. It heats the surface of the earth, heats the atmosphere. And that's one way that a cold object can become hot. Another way of transferring heat is by convection. And the best example of convection is like a boiling tub of water. And that's all that this is like, imagine the inside of a pot of water on the stove. You've got heat coming from the base. So that would be like coming from Earth's core through to the mantle and to the crust. And even though on a stovetop, you can get a rolling boil going, the convection in the earth is not at that kind of pace. It is much slower because we're talking about partially molten rocks. We're talking about very slow processes compared to what we see like on a stovetop. But the hot water is at the bottom. That becomes more buoyant because of the heat. The molecules are a lot more energetic. They're spread apart farther. They're moving around. That rises because of the buoyancy with the heat. The cold water that's sitting at the top starts to sink and replace that water that had moved up because it had been heated already. And so you get this kind of cycle going where cold water sinks, hot water rises. Even though the hot water rises, when it gets to the top, it's cooling off again because it's coming up into contact with the surface, with the air and with the cold water at the top of the pot. So that then sinks again and it heats up again. And so it gets this cycle going. That is one mechanism by which we can transfer heat from the center of the earth to the top of the mantle. And eventually, if we get an eruption, then to the surface. Okay. I promised I would stop. I'm still not at that diagram. Where is it? Okay, I'm not there yet. Okay, I promised to do a tiny bit of this on Thursday just to get us ahead a little bit, because now I'm gonna have to drop a topic at the end of the semester. I can already feel it coming on. Okay, I'm gonna leave it here because I promised I would, and I'm going to take questions about this first, and then I'm going to take questions about the lab for anyone who wants to stay for the office time, office hour, coffee break, whatever you want to call it. And if you need a break, go take a break and come back. I'll be here for half an hour. Okay, so if you've got to sign off and go do other things in your life, go ahead. Otherwise, hang out and you can listen to the answers to the questions. Thanks for coming, guys. Sorry about the technical difficulties.
Thank you.
Bye. See you Thursday, hopefully.
Earlier you were talking about granite, and I have some if you want to see.
Oh yeah, show me some rocks. Oh, nice. Where'd you get that?
Yosemite.
I hope it wasn't in the park. We'll just say in the Yosemite area.
It was 8th grade. I didn't know any better.
So do you want me to identify the minerals for you, or do you want to do that after we start these?
Sure, you can identify them.
Sorry, what'd you say?
You can identify them.
So it's a little hard to see, but the big black chunks, unless they have a really flat, shiny surface, those are probably hornblends. Those are an amphibole mineral. So it's a chain silicate, which means that you end up seeing like these like little long crystals in them, maybe. Mm-hmm. If you see flat, really shiny flecks of black, those are biotite. That's a mica. They might also be silvery, shiny flecks. Those would be a muscovite mica. I'm making up words. Do I see pink, or is it just kind of grayish color?
It's really just gray.
Okay, so if you see gray and translucent, kind of a little bit translucent, you're looking at quartz. So that ought to look kind of glassy. And if you're looking at an opaque white or even off-white, but opaque, most importantly, those are feldspars.
Okay.
So you've got a nice selection there, and I think we've got all of those minerals in the rock kit that comes, the rock and mineral kits that come. Cool.
Thank you.
You're welcome. Any questions about the topo lab, map lab?
I'm good.
Okay, cool.
I actually have one real quick. I just wanted to know if we needed to draw like any topo maps, like in the lab.
Well, not yet, though you probably will get a problem at some point that asks you to do something like this. So in order to like test your knowledge of like understanding contours, you might get a problem that like puts a point on a map and does something like this, where you got 219 feet, 175 feet, 188, 206, and 199. I don't know what kind of structure I'm making now. 170. And then like you could draw in with like contours to separate the 200s, like say 20-foot intervals or something like that, starting with 200 as being one. We can do a contour in like this, maybe something like that. Another contour at 180 might be something like this. So you kind of like draw in contours to explain the different points on the map. And if it was done more carefully, then you might see a map structure, like a hill come out, or a ridge or a valley or something like that. So that's one way that you might end up doing, making a topo map. But nothing complicated. Like,
Okay.
Were you hoping to?
I was just mostly just curious. So,
Okay.
well, at least for like this lab coming up. Well, from
Oh, in this
last
lab
week's.
itself.
Yeah.
Yeah, no, nothing that complicated.
Okay. Also, I might have turned in the pre-lab in late, but you said that late work is accepted, right?
Totally fine.
Okay.
I haven't even looked at those yet, so don't worry about it.
Okay. Okay. Thank you. I think yeah, that's all the questions. Oh wait, the quiz as well. I haven't done the quiz yet.
It's open all semester. You can take it whenever you can get to it.
Okay.
Just don't get too far behind, so that you can stay on track with everything. But like I said, if ever there's a problem, you gotta like skip something, like you just can't make it up, just let it go slide, because we dropped the 2 lowest scores.
Okay.